So this part here, this is the particle and wave sort of debate. This is going back to the late 1600s. We have two people. I'm sure the first person you recognize. And on the other side, let me make sure I try to spell this right. Huygens. Huygens, Christopher Huygens, and Isaac Newton. They're sort of the key figures of this debate. And as I said, the late 1600s, so about 350 years ago. And Newton is already, he was younger, but he's already a big deal. His Principia and all, like, his laws, which were, really quite amazing, right? Like, people actually thought, you needed to keep a force on something to keep it going with a constant speed. And that's still, like, one of the fun things teaching it, right? It's still sort of your intuition, which is interesting. Because a lot of things, like moving it across the desk, you actually have to keep pushing. So he was quite brilliant and a big deal. And he was a proponent of the particle theory, right? That, well, and he thought that it had to be some sort of particle. And that really had most people kind of just going with that and thinking that. And it really was this guy, Christopher Huygens, that really sort of pushed this wave theory, or started to really make, no pun intended, but waves with that. And so there were several, the real question that the scientists at the time and everyone was looking at, well, how do you explain certain phenomenon with this particular theory? So the first one you might look at is what we refer to as rectilinear propagation, i.e. it moves in a straight line, right? Light moves in a straight line. We know that. That's pretty well supported by this particle theory, right? Newton really had that. That was maybe the biggest thing. And reflection, right? This was really consistent with Newton's, wrong thing. This was consistent with Newton's third law, right? And conservation of momentum. Right, we can sort of see, okay, yeah, this is what would happen. The first one I didn't really mention, but this is kind of like Newton's first and second law. Right, you can imagine it's a particle while it's moving unless acted upon by some force. Right, that would sort of explain that. We can go to some other properties. Refraction, which we kind of looked at. And again, I'd sort of like the two-wheel wagon or whatever, but Huygens kind of had him on that one, right? That seems like, if you look at these sort of wave fronts hitting, if you can allow like this wave to be kind of spread out, then you would say, well, these waves, right? These waves hit first, right? This part of the wave encounters the slower medium first. So that was kind of, good support there, right? You've got waves, that would make sense if you had something like that. It's you can imagine it's kind of a wave front. And another diffraction that we looked at, right? If you have kind of a small opening like this relative to the wavelength, then that ends up acting like a point source, right? We saw examples of this with water waves, but bear in mind, like we see this with light as well, right? If you have a really small opening and light going through it, or like a little pinhole, right? It acts just like a point source. So these were some really good, beliefs or reasons for why light would be a wave. So it was kind of a debate. This did seem to go on. If you go back to Newton and you look at refraction, right, he sort of said, well, this is kind of consistent with ballistics, right? So I'll say that, yeah, this is, consistent, or this was his claim, consistent with ballistics when going into a slower medium. The challenge here, right? So that is, you've got some sort of particle here, which I didn't really draw. If you give it, and maybe that's not even a really good representation, right? You kind of have to give it some sort of shit. You can imagine like a bullet or something like that, right? It's sort of part of it hits first, it may change its trajectory, right? So you're having to give it some dimensionality here and everything. But he said that would work. Diffraction. They said, well, you can kind of imagine, particles hitting the side of a wall, right? If you can imagine all these light particles hitting something like this, well, maybe they somewhat bounce, they're bouncing into each other, they bounce off the side of the wall. That would kind of work, right? So at this point, we've got, these are a bit, which theory do you like? So, okay, those are a bit weak, but if you go to kind of the first two, I said Newton had some pretty good logic here, right? Rectilinear propagation and reflection. So Huygens kind of had to look at the rectilinear propagation, right? That it goes in a straight line, and he said, well, the wave fronts all sort of move together, right? So it's not just one wave, right? When you have a source of light, right? It's giving off lots and lots of light waves, if you will, and so. But the wave fronts, right? As soon as you turn it on, and there's a bunch of them that go out, they all go together, right? So that's sort of what you're looking at there. So we can see that, and then reflection. It's basically saying that every point of the wave gets reflected, one after the other. So if you kind of look at, here's the incident wave, right? You could pick, so this point right here sort of gets reflected, right? Then this point here gets reflected, and so on and so forth, right? So he said, well, that would work, right? As the wave is sort of hitting it, each part gets reflected in turn and gets, reflected so that the angle of incidence equals the angle of reflection. Just to write that down. At this time, Huygens was kind of considered the winner. This sort of won out. This is kind of a big deal. And as I said, you had some really good cases here, like refraction and diffraction. And the others were sort of, okay. It was a little bit, things were a little bit conflicted and whatnot, but that seemed to be the main thing. The other thing that really, really made people think it was a wave, we kind of didn't mention, but I will show you. This brings us to Thomas Young's double slit experiment. I should have put in, I'm not exactly sure of the date. I want to say 1803. But like I said, this is like well over 100, probably about 130 years or so after this debate where we were just looking at, right? We sort of come to Young's double slit experiment, which is kind of a cool experiment. So the idea here is you get, now just like before, and I got a question about this, but I didn't push it enough, right? We're dealing here with like monochromatic light, like that is it's all has the same wavelength. When we were looking before at those nodal lines and that, right, we were considering, the 2 point sources of water, right? They had the same, it was the same wavelength, right? It's in the same medium. It's the right. So that's kind of a real key here. But yeah, you take this, I guess maybe red light, and you shine it through like a very small opening. We saw that gives us diffraction, right? It acts as a point source here for the light. And you can shine this on a screen. Now, what do you really get when you look at this screen? Or like, where is it most intense? The light, that is. Right? Where is it brightest? You've got your light coming out from this point right here. It's acting as a point source. We've got a screen. Now, let me sort of mention here. We should say this is a top view, if you will. All right, so you can imagine you're sort of looking down, and we're kind of here looking at the top of the screen. Okay, and we just want to see like, well, at what point along the length of the screen is it brightest? Is it all sort of like, if I sort of represent the intensity of the light, does it kind of look like that? Is it just bright everywhere on the screen, or would it be a little bit brighter at one location? Right. Okay. Yeah. The middle. Exactly. Right. If you shone this here, right, just because more light's going to reach it, and so you end up seeing it looks kind of like a bell curve, right? It's most, and so this represents the intensity of the light, if you will. Right. And so I'm just sort of drawing it relative to the surface. So this, however far this is from the screen, just represents sort of the intensity or how much light is reaching that point, right? And so you can see as it falls off here, what I'm trying to show you here is right. Not a lot of light reaches that. I think that should sort of make sense just intuitively if you've ever shone a light or you get a flashlight. This would be more of a 3D effect. I'm just sort of showing it in 2D, right? But if you shine a light on a spot on a wall, right, it's bright here and then it gets a little less bright, right? It gets fainter and fainter as you move away, right? So that's okay. Now, here's what we do. We get 2 slits instead of just one, right? And so this here is sort of showing you get your light, your monochromatic light. You can send it through a point source first, but it doesn't really matter. Again, it's all the same light. And now you've got 2 sources. So, well, you can tell me. Basically, what you would expect, I imagine, is if you only had slit 1 open, right, you'd have something that looked, let's just say, kind of like this. And if you only had slit 2 open, you'd probably have something that looked like that. Right? And so you would reason that if you've got both slits open, let me try to find something here. Both slits open, then what you kind of see is, right, something like that, right? This is if this darker one represents the total light that you see, right? With 2 slits, am I incorrect in assuming that this is what you would expect, right? You would expect the light to be most intense right here or brightest right there, and then you would expect it to sort of peter out, right? You would get, again, a superposition, which is a common thing in physics. All right, so I'll just say this is the expected, right? Well, like I said, you get 2 like if you can imagine just 2 sources of light here, like 2 flashlights, you kind of expect something like that, and that's again kind of consistent. That's that's what expected. Now, what actually happens when you do this experiment? Well, you do get kind of a bright spot here in the middle, I gotta say. Which let's see if I can draw it. And then a dark spot, and then a bright spot, and then another. They do go down in brightness a little bit, but and you get the same thing on the other side, right? That's what happened, where you have all of these, right, nodes here, i.e. dark spots. Which is, again, just a really cool thing to see. And this was really like, okay, we can declare Huygens the winner, and that's right. This is a wave, right? It's got to be a wave. You how can you do that with a particle, right? Right? You don't. It's not like I throw 2 balls at the wall and one cancels out the other, right? But you do see this with waves, right? You get superposition, and so you say, well, what has to be happening here at these nodes then is one of the wave that's coming from this one and the wave that's coming from that one are off by a half lambda or 1.5 lambda or 2.5 lambda or something, right? One of those multiples. And that's what makes them out of phase at that point. And so you get a node, you get a spot that is completely dark, right? And then you get these other spots where you've got, constructive interference, let's say here, I don't know if I need those two there. And once again, we can do some of the math. This is actually a little bit similar to what we were looking at before with 2D interference, right? We're effectively finding a point P. We've got two sources, right? Which in this case is kind of like our slits. And there's a certain distance P away. And once again, usually it is the case that the wavelength is small enough and the distance, which we're representing as L here, right, the distance to the screen, is long enough that we can make some sort of small angle approximations. And so it should work out. So again, you've got I didn't really write it here, but you can imagine you've got your light source here, right, and all your light sort of going this way. I don't think I needed any of those, but all right, so there's our light source. And what we're interested in figuring out is what should the angle here be, right? If we look at our screen, remember we're going to get some pattern here where, okay, we're going to have a maximum somewhere here, and it's going to go down. And then we're going to have maybe another maximum, and then another. And so P is going to represent one of our nodal points here, right? We've got to know. So we want to know like what angle should we expect this at, right? This here would be our central max. Well, it's just a little bit of geometry. We can do that. And so, and this part here is already partially, like the numbers are all sort of filled in here or whatever, right? But what's important here is we have this distance. So we've got a slit on the top here. And the light that goes through that slit goes this distance here, which we're writing as L1, right, from the slit to the point. And on the bottom, we have, if light goes through the bottom slit, it travels this distance, which is L2. So we can sort of put together a triangle here, and we can say, well, assume this point here represents the point where L2 would be identical to L1. So we have this extra bit right here, which we just draw, which we'll just call delta L, right? This is the extra bit that the one on the bottom has gone to get to the point P. We can use this triangle right here. You can see that in there. Or maybe I get rid of that now. We can use that triangle and just do some trigonometry. Again, we can assume this is a right triangle, which is a pretty good approximation. It's a slight approximation, but it's a pretty good one. And then we can say, well, the sine of theta, right, would be the opposite side, which is what we're calling delta L, over the hypotenuse of this, which would be D. And so you can see we just multiply both sides by D, and that's how we get this expression here. Right, so that's our delta L. And then we can just look at what has to happen for what we want. If we want a maxima or we want a minima. And we're kind of doing the same thing we did earlier where we're saying, look, and again, you have to look at this, just the scale this is drawn on, it's hard to tell. But in reality, we're saying these slits are very close together. These are like a millimeter or two apart. And the distance from the slits to the screen is like a meter or so, right? So much, like 1,000 times farther. Small angle approximations is very good to do. So when you're looking at this, really, it's like, okay, this point here might as well represent the point where both slits are. Right? And so when we're doing the distance from the slits to the screen, right, we could just sort of say, well, basically it's just like one line. I don't really have to draw L1, L2, and L1. And so if we do that, then we can say that so what this is showing here is we're saying, well, effectively, if we just make one line that goes from the center, if you will, to the point P, and then we look at, and that's the one that's drawn on top. So we say we look at the angle here, theta. If we make a triangle here, and again, imagine that coming from the center, then that angle theta would be identical to this angle theta here if we make that assumption. And that's similar to what we did earlier, where you could say, well, do a little bigger. We could say this distance here where D is perpendicular to this distance here to the screen, and this distance here from what we're saying is from the center would be perpendicular to this distance here, or to that line there, right? Those are perpendicular, these are perpendicular, right? So they're both perpendicular, and whatever this angle here is, then this angle here is, right? From green to blue is the same. So some assumptions are, again, small angle, but given the size and how far away this thing is, it works pretty well. We can say those are both the same angle. And then we can look at this and say, okay, if we want a maxima, right, we want constructive interference. I guess we'll look at this first. What has to be the case, right? Well, delta L, right, that extra distance, like if it's the center maxima, they both go the same distance, right? At this point here, both of them go the same distance. But for any other ones, if we're getting a maxima like here, then it must be the case that the one from the slit on the bottom has gone an extra full wavelength. That would get them completely back in phase, right? So delta L is lambda, or better yet, some multiple, right? And just let me see. I guess we'll use M for points of maxima. Right, so any multiple of lambda. And then if we use that trigonometry here, we use this, we already saw that delta L is d sine theta. So that means we can write that as d sine theta is just equal to m lambda. And we should stipulate here that m is any integer. Or I guess I could just say whole number, but since most people understand integer a little better, I'll just write it that way. Okay. But then if we want a minima, right, that means we want waves to be 1/2 wavelength out of phase, right? So one of them could have gone a half wavelength, 1.5, 2.5 extra wavelengths, whatever that is. We can do the same thing. And I guess here I could just replace that and say, or d, let's say d sine theta, because that's still the extra bit delta L. But it's some multiple of, so basically it's lambda over 2 plus any, I'll use n if it's a node, plus n lambda, right? So essentially saying it has to go this lambda over 2 bit, but it could go, so n could be 0, right? Or n could be, in the way I've drawn it right here, right? Or it could be, if n is 1, that gives you 1.5 or 2.5 or whatever. Or, and I think the book writes it slightly different, you could write it as d sine theta equals n minus a half, which was kind of like the formula we used earlier. But in this case, n starts at 1, right? Because the first one, which is just a half, you'd have to put in 1 for n. So you could use this, and then you could just stipulate that n is any integer. Just as with the other one. I would write these down. Right? I mean, do make a sketch, whatever, where it comes from. But, there are ones where you don't want to kind of have to think of this. Sometimes if it's a dynamics problem or something, right? Like, how far up does something go? You maybe memorize some of the equations of motion or whatever. But these can get a bit, you've got maxima and minima, and it can get a bit much. So I would try to tuck those away, or just have them available if I'm answering any questions. Here's kind of what something like that might look like. I tried to get an actual picture because I can't really do the demo here for you. And that's basically what you would see, right? And you can see, of course, it's all the same color light, but you do get these nodes, right? You do get these points where there's like no light, and kind of cool. Just like before, where we were looking at distances. Sometimes you might actually want to know the distance along the screen, right? You can see right here, like maybe you can. This is the stuff you could actually measure, right? You could say, well, let me measure the length from the slits to the screen, and then let me measure the distance from the center of the screen to the point where that node is, or in this case, where this anti-node is, right? These ones are maxima, right? And we can kind of figure out where that would have to be. It's not written in here, and I guess we don't really need it, but do remember this distance here was D. Sorry. Right, that was sort of the separation between the slits, was what we were calling a distance D. And this one's maybe a little bit better at showing you how that distance between the two slits is pretty small relative to the length, and even this is probably not very well to scale. So we've got our equation here, d sine theta equals m lambda. That's the one I just wrote in the last page. I know pretty much verbatim. And I want to work delta x into this, right? But we can actually, because of these long distances and how small some of these angles are, we can sort of approximate this a little bit more. If you look at, I guess, let's just look at the first one, x1 over L, right? We can say, well, sine theta, right, is equal to x1 over L. And then, well, what if I asked you to... Oh, sorry. That's not true, is it? It's tan theta, right? Tan theta is the opposite side over the adjacent. But, although the point is that if you've got a really, really small angle, right, for small... So you've got a really, really small angle. And you can kind of see that, right? Because the sine of theta is this really, really small bit over the hypotenuse here, right? And then the tan of theta is that same really, really small bit over L, which L and H are really, really close. And if you do this, or like you can punch this into a calculator, even with really small angles, like 1 or 2 degrees, you're basically going to get the same result, probably even really close or very little error up to about 5 degrees, right? So you can use this approximation, in which case, right, for sine theta, we can take this and just plop it in there. We can say, well, that means D times x1 over L, just replacing sine theta with that, equals m times lambda. Now, I really should have written this as xm, since this is the first one here, but really it's the x2 a maxima, right? And then I can isolate that, multiply both sides by L, and divide both sides by D, and I get m L lambda. divided by d. And that gives me the distance, if you will, I have to go to get whatever maxima. So xm, so m could be 1, 2, 3, whatever you want, and that will give you about the distance you need to go to get that. I didn't do a sketch for this, but if you go back to the first, so suppose we want the equation for minima, right? You can take, it's very similar to this equation up here, right? The only difference is we're using an n because we want to use an n if it's a node, and we have a slightly different equation because it has to be like a half lambda, not a full lambda, right? Or 1.5, 2.5, etc. But we can do exactly the same thing, and we can replace sine theta with x over L. So we can say that goes to dx, but I'll write it as xn now, over L equals n minus half and then I can do the same thing, multiply both sides by L, divide both sides by D, and I get xn equals, I guess it doesn't matter if I write this first or second, n minus a half times lambda L lambda over D. And again, you can kind of compare and contrast these. Very similar, right? L lambda over D, only for a maxima, it's just an M, and for a minima, it's n minus a half, or I guess for a node, better to remember it that way. For this example, we have it's a double slit experiment. We're using 700 nanometer red light. So that we're given, the nanometers is just 10 to the negative 9 of a meter. So you can always, anytime you get something like that, just as a general thing, right, if you see a nano, right, you can just replace that with 700 times 10 to the negative 9, right? And so that's going to change it a little bit, but since it's 700, then it works out that it's 7 times 10 to the negative 7. Right, so that's the wavelength of the light that's going here. We're told the distance to the screen is 2.8 meters, and that the slits are separated by 0.15 millimeters. So I convert it, so there's D down there, 0.15 millimeters, but that's 1.5 times 10 to the negative 4 meters. So obviously, yeah, I would convert this stuff to, I didn't write the units here, but I would convert this to SI units, or just everything the same, because you're going to get millimeters, meters, centimeters. Just as long as you're consistent, it should work. So here's my little sketch of that. There's my my screen on the other side, and I tried to draw roughly the interference pattern that we would see. And it's not perfect, but you get the idea. You know what happens. And we want to figure out xm, right? We want to figure out the distance to the first maxima. Now, it does say successive in the question, right? It doesn't say the first, but it should be the same distance to each one, right? If you just look at that equation, remember we replaced sine theta and all that, and you go down here, right? All that's happening in this equation is we just change m from 1 to 2, right? L stays the same, lambda and D stay the same. So the next one would just be double that, triple that, right? So they're all the same distance. That should help us out. And I just made a note there, right, that obviously m will equal 1 for the first maxima. So I always try, even if you don't show it on a test or something, like I always find a sketch if something helps. And if you're asked, definitely do it. But so for this, you plug in the numbers for the equation we already have, and I get 1.306, well, 6666666, but times 10 to the negative 2. Or, again, you could just convert that to centimeters and say that's roughly 1.31 centimeters. In other words, that's about 1.3 centimeters from here to here, like that I would expect every 1.3 centimeters roughly I see a maximum. And by contrast, B asks, how would the distance be different for minima, right? And if you look at this, it's like, well, every point, every maxima, if you will, right, is going to be, it's going to be 1.3 centimeters from here to here, another 1.3 centimeters, and the minima, right, are all exactly in the middle. Right? So it would stand to reason that they would all be separated by the same distance, right? But the first one, right? So if you look at the first maxima, occurs the same. Whoa, sorry. The first maxima occurs this distance, which is the same distance to the second one. But for minima, it's different, right? Here's my center line, if you will, right? The first minima occurs at a half that distance. Right? So that's really what I have to look for here, right? I started to write that down. So the first minima occurs at xm over 2, right? Whatever half that is. So you can just take that distance there, which we said was 1.31 in centimeters, and divide that by 2 and get 0.665. Right? So you'd have to go up or down 0.665 centimeters to get the first maxima on either side. And then the rest occur every 1.31 centimeters after. And then part C. So for part C is kind of a little bit of a thinking question, I think, right? How would this be different if I used blue light? Would it be different? Absolutely, right? It would have a different wavelength. We know the wavelength is um, associated with the color, right? Yeah, so for me, I mean, this is one where I might sort of like trust the equation and then convince myself of why that is, which is sometimes a weird way to do it. But even if I get conceptual questions or something like that, I sometimes find that kind of helpful. So for part C, I want to look at blue light. Move that over a bit. So I already made this. Hopefully you've seen this before, right? Remember Roy G. Biv, the different colors of the visible spectrum. And we know red light is about 700 nanometers in terms of the wavelength. And then we get orange, yellow, green, blue, indigo, violet. As we move across the spectrum, right, they become more energetic and their wavelength decreases, right? So blue light would roughly have a wavelength of about 450 nanometers, right? So we can say, right, lambda would be shorter. And again, if we just sort of trust the equation, we just kind of go up here and say, well, the distance, which is xm, which we're trying to find, if we put in a smaller value for lambda, then xm is going to be smaller, right? Because they're both in the numerator, right? Xm is technically over 1. So we say, well, if we just trust the equation, we just say, well, then that means we'll get closer together, right? The distances will get shorter, and which means maxima and minima get closer together. And then from there, I would sort of go back and try to, if I want to really try to understand this conceptually, or, wait, what's going on? Why is that? right? Like, let me just make sure this does make sense or whatever. And then what I say is, well, what makes this happen in the first place? And maybe I've already got a nice diagram here. Let's go back. Let's go back over here even, right? What makes this happen? Well, the distance, right? The delta L, right? Has to be a certain amount of wavelengths, right? When delta L is, one wavelength, you get a maxima, right? So if you decrease that wavelength, then you don't have to go as far along the screen, right? That point should happen closer because again, the delta L necessary would be smaller because it would have to be a wavelength.